Thank you very much, Charles. It's a real pleasure to be here. What I'm going to tell you today, I'm not going to talk about cold atoms or qubits. I noticed that the Quantum Institute is really, most of the work is in that direction, so you're going to hear about something that is totally different. I'm going to tell you about what happens in imperfect graphene. So we all know the wonderful things that graphene is when it's pristine. What I'm going to tell you about is what happens when you pluck out one carbon atom and you look at the vacancy that's left behind. And there's two things that we're going to be looking at. One is the vacancy acquires a charge, and we can actually tune that charge gradually from where you have standard Klein tunneling to where you get something that is we call atomic collapse, which is the equivalent to atomic collapse in atoms. And I'm going to tell you all about what that means. And if time permits, and depending on the number of questions, I'm going to get to the magnetic moment. The vacancy has a magnetic moment of about 1.5 Bohr magnetons. And under certain conditions, we can see Kondo screening of that magnetic moment by the conduction electrons. So let me start. I think you're all familiar with all the wonderful, this is a partial list of graphene superlatives when it is a perfect lattice. There are electronic properties, mechanical properties, highest current density at room temperature, highest intrinsic mobility, conducts electricity and the limit of no electrons, lightest charge carrier, zero mass, transparent, one atom thick layer absorbs 2.3% of light, strongly diamagnetic, and then there's these wonderful mechanical properties. It's the thinnest imaginable and strongest material ever measured, stiffest known material, most stretchable crystal. You can stretch it elastically up to 25% without it breaking. Completely impermeable, even helium atoms can't go through it, and so on and so forth. What I'm going to focus on today are two properties. One is what happens to this property, highest intrinsic mobility, when we have vacancies, and the other one is what happens to the magnetism, to the diamagnetism. Here are the two properties. So highest intrinsic mobility. The reason that mobility is so high for electrons in graphene is because they are chiral. So their pseudo-spin, what we call here, is aligned or oppositely aligned to the momentum. So let's say that we have an electron coming here from the left onto this electrostatic barrier. It cannot scatter back because it's chiral. So there are selection rules against backscattering, which I'm going to get to. And as a result, it just has to go through the barrier. It has to deal with it. It turns into a hole under the barrier and comes out as an electron. This is this well-known Klein tunneling phenomenon. And this is very beautiful, but as a result, there are all sorts of things that we cannot do with electrons in graphene. For example, we cannot confine them by electrostatic potential. No quantum dots, no switching, no guiding. So in a sense, this is kind of a nuisance, and we would like sometimes to get rid of this property. The other property is it's diamagnetism. It's one of the most diamagnetic materials known. And the reason is this famous Lieb theorem, which says that the spin of a half-filled bipartite lattice, bipartite means that it has two kinds of atoms in it, with the Na and Nb populated state is equal to 1/2 times the difference between the populations of the two sublattices. And as you'll see in a moment, graphene has equal number, the two sublattices are equally populated, and as a result, pristine graphene, if you exclude the boundaries, the spin is zero, no magnetic moment. Now, this actually issue was a long-standing issue. People in the 2000s started reporting observation of magnetism in graphite, and there were huge. It was a very controversial issue. It was not clear where it's coming from. A Nature paper was retracted because people claimed they saw ferromagnetism, and then the argument was that in fact they were looking at impurities. We will see in fact why it is possible to make graphene magnetic and under what circumstances. So this is actually nice to see. If you look at diamagnetic materials, of course, superconductors are most diamagnetic, but graphene is somewhere here. Pyrolytic carbon is the largest non-superconducting diamagnetic material, and so on and so forth. If you look at Wikipedia, you're going to see this list. So let me start with graphene. In the graphene, the valence electrons hybridize into sp2 orbitals when they make chemical bonds. So you have 3 electrons that are in the plane and 1 electron that sticks out of the plane. So 2 electrons here are bound to the next nearest neighbors. If you end the other one here with hydrogen, you get a beautiful benzene, stable molecule. But if you replace the hydrogen, let's say, with another carbon atom, you can tile space with this honeycomb structure here. And it's these sigma bonds, which are the strongest in nature, that give graphene its strength. They give it its stiffness and its flatness. The pi orbitals, which is the one orbital that sticks out of the plane, give it its electronic properties. So we have an electron that is wandering on the sublattice, and its properties are controlled by the geometry of this sublattice, of this lattice. Now, there are 3 ingredients that go into the electronic properties of graphene. The fact that it's 2-dimensional, the fact that the structure is honeycomb, and honeycomb structure, it's not a Bravais lattice. It consists of 2 interpenetrating Bravais lattice, 2 triangular lattice, and as a result, you cannot have a block wave function. You have to have 2 block wave functions describing the electrons on this sublattice. And the third important ingredient is that the populations are identical. If they were not identical, you will have a gap system, like boron nitride, for example. So if you see here, we have the 2 sublattices are the green ones. So green carbon atoms have a neighbor south, and the red carbon and no neighbor north, and the red carbon atoms have a neighbor north but no south. And these are 2 separate triangular sublattices. What are the consequences of that? If you write the wave function of an electron in graphene, you have to write it as a linear combination of 2 block functions, the green ones and the red ones, and the 2 projections here look like a spinner. So in fact, we have a new degree of freedom, which we call pseudospin, and which behaves in many ways the same as a spin, except that if you have a Pauli matrix operating on this instead of operating on spin, it operates on the sublattice degree of freedom. So if you do a tight binding calculation, the band structure looks like this. It consists of 2 cones here, what we call Dirac cones, and the 2 corners of the Brillouin zone. The plane here indicates the Fermi surface, and that is at charge neutrality. The Fermi surface sits exactly at the apices of these cones. Everything that above it is electrons. Everything below it would be hole excitations. The momentum, if you measure the momentum relative to these apices, relative to the Dirac points, the electronic properties are described by this Dirac-Weil equation. So here is the effective Hamiltonian. Sigma is the Pauli matrix, but remember it operates on the sublattice degree of freedom, not on spin. P is the momentum measured relative to the K point, and VF is the slope of this cone, or the Fermi velocity. And the 2 cones are related by time reversal symmetry, so they're time reversal partners of each other. Now, this equation is exactly the same equation that describes neutrinos before they had mass. And we're actually not totally sure whether or not electrons in graphene have mass. So if the dispersion relation here is linear. The energy is proportional to the momentum, and the prefactor is the Fermi velocity. the Fermi velocity is about 300 times smaller than the speed of light. It's determined by the product of the lattice constant and the hopping parameter between nearest neighbors. And this is so the speed of these neutrinos is much slower, 300 times slower than the speed of light. And of course, the mass is 0 because the dispersion is linear rather than quadratic. So this is why we call them massless Dirac fermion. There's something interesting. If you look at this Hamiltonian, you see that sigma dot p is the chirality operator. So chirality is a good quantum number. And that is the projection of the pseudo-spin on the direction of the momentum. So in this cone, the projection is it's parallel to the momentum. In this cone, it is anti-parallel to the momentum. So you have two types of chiralities here. Unlike neutrinos, they're both types. In neutrinos, you only have left-handed neutrinos. So chirality is conserved, and as a result, you cannot scatter between the two cones. So you cannot backscatter between the two cones. Something else that is conserved, see that I have a color code here. Green means the green sublattice, red means the red sublattice. And as a result, you cannot have backscattering within a cone either. Because the wave function would have to move from the green sublattice to the red sublattice. So there's no backscattering. So as a result, we have this strong selection rule against backscattering, and that's why the carrier mobility is high, and that's why we cannot confine them with electrostatic potentials. Now, unlike neutrinos, you can pile these things up. We can look at the density of states. And the conical band structure here directly translates into a density of states, which is linear and vanishes here at the Dirac point. So density of state at the Dirac point is 0. Unlike in regular metals, where it's roughly constant, you have very small 0 density of state at the Dirac point. And as a result, if we make a device, this is a typical device, graphene, is sitting on the highly doped silicon gate with a silicon dioxide insulator in between, roughly 300 nanometer thick. You apply a gate voltage. It's very easy to add or subtract, take away electrons. So if you start out with a sample here and apply a gate voltage, positive gate voltage moves the Fermi energy up into the electron sector. Negative gate voltage moves the Fermi energy into the hole sector. A very easy way to dial the position of your Fermi energy. And it's actually quite cheap. For this geometry here, every volt of gate voltage buys you about 7 times 10 to the 10th carriers per centimeter square. So it's very easy to change the Fermi energy. Can't do that with regular metals. Another interesting thing that happens if you apply a magnetic field perpendicular to the layer, you get a sequence of Landau levels. Now, because of the conical dispersion, the Landau levels, unlike in non-relativistic electrons where the Landau levels are equally spaced, here they are spaced like they go like the square root of the magnetic field and the Landau level index. So this is the bunch of flat states. And here we have electron sector, hole sector. Unlike non-relativistic electron and non-chiral electron, we have a state here exactly at 0 energy, whereas in non-relativistic electrons, there is a gap here at 0. This is just comes from the 0-point energy. And this is a very special state. It consists of electrons and hole states. And there are very interesting things that one can do in the n equals 0 Landau level, excitonic states, and so on and so forth. So this is a direct consequence of the chirality. Now let me go back to what went into this band structure. As I said, there's 3 ingredients. Now, notice none of the 3 ingredients says carbon. And in fact, it doesn't have to be carbon. As long as these 3 ingredients are satisfied, we can make graphene out of other things. So, and this is the carbon in 2004, silicene, out of germanium, stannine. The years are either when it was discovered or when it was proposed. So there are other kinds of graphene that one can make as long as you have a honeycomb structure, as long as you have some overlap integral, two-dimensionality, and identical population. The moment populations are different, it's a totally different system. You open a gap. So actually, the three ingredients don't say atom either, so it doesn't have to be atoms. And here's an example where you make graphene. This was done in Harry Manoharan's group, where you take carbon monoxide molecules, and you have very diligent students, and they arrange each atom at the corners of a triangle. So the atom sits in the dark regions here. The wave function is this honeycomb. And you take the density of state, and it looks exactly like graphene. And of course, the Fermi velocity is renormalized because the hopping parameter is different. But it's not too different from graphene. It's 3 times 10 to the fifth meters per second. But you can also make it with cold atoms. And people have made optical lattices that look like graphene. And this is an Austrian group. And again, the band structure looks like that of graphene. People have made a similar band structure with microwave cavities, and so on and so forth. So as long as you satisfy this condition, you can get the same kind of band structure. Now, I was talking about the neutrinos. Here we have charged particles, and we know that the fine structure constant controls the electromagnetic interaction. And the fine structure constant here is E squared over H bar over C. It's a small number. The electromagnetic interaction is very weak. One way to look at it, if you write the Rydberg, and if you write it in units that I like to write it in, so it's the rest mass of the electrons times the charge of the nucleus times the fine structure constant square, you see immediately how small of a number it is. For hydrogen, Z equals 1, the Rydberg is only 13.6 electron volts, which is a tiny fraction of the rest mass of the electron, which is a half MeV. So we have this periodic table. Most of the light elements are very well described by a simple Bohr atom picture. When you get to the heavier elements in the periodic table, like to 100, you have to take into account the fact that you're getting close to the 0-point energy, and relativistic effects come in. So in graphene, the Coulomb interaction for graphene that sit inside the plane at low energies is governed again by a renormalized fine structure constant. And you replace C here by the Fermi velocity, and this is a dielectric constant. And now the fine structure constant is huge, is of the order 1. So that gives you the opportunity to study physics at large fine structure constants, which we would not be able to do at all in this world. So how do we do that? So I'm going next to discussing a little bit of what you expect to see when alpha is large. So let me start with the Bohr atom. So you have a massive electron in a 1 over r potential. You write the total energy. You throw in some quantum mechanics. And you write the total energy as a function of position. Now, rho here is the distance from the center of the nucleus in units of, of the Compton wavelength. So if I use the Compton wavelengths, I can very nicely use here dimensionless units. And beta here is the so-called Coulomb coupling constant, is Z, charge of the nucleus, times the fine structure constant. And you see immediately that the kinetic energy diverges as you go to the origin as 1 over rho squared, and the potential energy goes like minus 1 over rho. And of course, that gives you a minimum, which defines the characteristic energy and the characteristic length scale, which is the Bohr radius, which is just the Compton wavelength divided by beta, and the Rydberg energy, which I just mentioned, 1/2 mc squared times beta squared. So then you get to this nice series, a nice Rydberg series that we all know and love. When beta is much smaller than 1, this is all very accurate, and it works very well. It's a good approximation to the problem. And now let's walk up in the periodic table to heavier nuclei. So the Rydberg sinks down, and eventually it gets close to the Dirac continuum, and all hell breaks loose. We can no longer use these approximations. Now you have to write the relativistic expression for the momentum, and you have to take into account the rest mass of the electron. So what happens there? So instead of the Rydberg looking like I showed before, it's actually a two-line calculation. It looks like mc squared multiplied by 1 minus z alpha squared. Dirac already noticed this back in the 1928. So you see, all works well until you get to the critical value when the charge of the nucleus is 137. You get an imaginary solution. Your Hamiltonian becomes non-Hermitian. You can't work there anymore. So in fact, this gives us a kind of a hard limit on the length of the periodic table. Of course, it stops much earlier because nuclei become unstable. However, in the 50s, people realized that you can regularize this problem. You put a finite size nucleus. If you include that, then you do have solutions for Z that are larger than 137. But what happens, so the critical value shoots up to 170, but what happens is something very interesting beyond 170. The electron sinks into the nucleus. It falls into the nucleus. What happens is that when the electric field is so strong, when we get down here, you spontaneously generate electron-positron pairs out of the vacuum because you're sinking into the Dirac continuum. And if you have an atom, if your electron sinks into the nucleus, it'll generate, so you have one electron that goes into the nucleus, it neutralizes one charge, and then you have a pair, and you have another one that comes in, so 2 electrons and 1 positron emitted. So here's the electrons falling into the nucleus and the positron emitted. And people were looking for, our nuclear physics colleagues were trying to see the spontaneous positron generation for decades by colliding heavy nuclei, heavy uranium nuclei together to see this, and it was very difficult because we don't have heavy enough nuclei. So what happens with graphene when alpha is large? Before I get there, this is our periodic table here. You increase beta, you increase the charge. This is where our atoms live. This is the mass gap here, 2 mc squared. One is where the Dirac limit, 137. And when you got beyond 170, this is the theoretical end of the periodic table, and positron emission here. So let's go to graphene. If you take the limit, the same problem, another few lines of algebra, you take the mass to 0 and the velocity to the Fermi velocity, the dependence of the energy on distance looks like this. So one thing that you will notice immediately is that in this case, the potential and the kinetic energy scale the same way. This is a scale-free problem. We no longer have a minimum that defines a characteristic energy scale or distance. It's a completely scale-free problem, and this is what it looks like. So here you see immediately when Z alpha is less than a half, the energy is positive, and basically the electrons go, this is a Klein tunneling regime. The electron just goes through, it cannot be confined by this positive potential. And now, but when Z alpha is larger than a half, we have a phase transition. The sign of the energy changes from positive to negative. And because alpha is a large number, it happens at the critical charge of basically 1. Okay, you don't have to wait to get to 170. And this is what it is. So you get a sequence of quasi-bound state. This is the equivalent of the 1s in the Bohr atom, 2s, 3s. There are several differences. One is that it's not really a bound state, it's a quasi-bound state. You can still tunnel out to the Dirac continuum here. So you have electrons and holes sitting at each energy. Another very interesting thing, and it's direct consequence of the scale-free property of this problem, is that the energy goes like it's exponential in n as opposed to 1 over n squared in the usual Rydberg series, and the ratio between two adjacent states is a number, e to the minus pi over the angular momentum quantum number. And this is what is interesting, and this was pointed out by Efimov in the 70s, is that this sequence, the ratio is the same regardless of whether you're in 1 dimension or in 2 dimensions. So when you have a 1 over r squared, for the Schrödinger equation, you're going to be looking at a 1 over r squared potential. And people in cold atoms were actually able to simulate that and see the hints of this Efimov series in cold atoms. Yes?
So that kappa at the denominator is dielectric constant?
The kappa is the effective dielectric constant. So if you're sitting on silicon dioxide with dielectric constant 4 and you have vacuum on top, so the effective dielectric constant from that is 2.5. However, you have to take also into account the dielectric constant that comes from the screening of the electrons in graphene.
But since this is a semi-metal, let's say it's a metal, then how do you even define dielectric constant?
Well, you can define dielectric constant in graphite, or it's just a matter of the screening. But what we look at is the dielectric constant from the environment. It's 2.5. And then you have a random phase approximation that tells you dielectric constant of the 2D electron system is about 3, but measurements are all over the mess. Yes, you can have a dielectric constant. It comes from the screening. So if we do the same diagram as before, energy as a function of the charge. So when beta or V alpha is less than a half, we have no bound state. This is where the Dirac point is. And as you increase the charge, you start having this quasi-bound state, 1s, 2s, and so forth. And this is the equivalent of the atomic collapse in atoms, except that the critical charge is 1. It's actually interesting to compare the two. So the gap here, the mass gap that we have in atoms disappears. So the equivalent of the periodic table doesn't exist here. So we have the unbound region, which is here, and we have the atomic collapse region, which is here. Now, in 2013, a group at Berkeley took calcium dimers, and they piled them up one on top of the other. They have charge, and they looked at the density of states. And when they got to 5 calcium dimer, they were able to see a state, a peak, which they identified as something sitting right here. The problem with doing that is very hard to pile up the charge with external charge. It's going to basically, how are you going to hold 5 calcium dimer in one spot, piling them on top of each other? It's not clear, but they were able to do that. So we did it in a different way. And I'm going to now move on to telling you how we did it. And we start with vacancies. So, so what happens when you pluck out a carbon atom from a graphene sheet? So this is a pristine sheet, an undamaged sheet. So this is the topography here. This is the density of state that we've seen. It's linear and vanishes at the Dirac point here. These are pi states. The sigma states are sitting much, much below, and they're more strongly bound. Now we are plucking out one carbon atom. There's 2 things that happen. One, you have a crystal field, and then you have a Jahn-Teller distortion. And this is what it finally ends up looking. So when you pluck out a carbon atom, you've taken out 4 electrons out of the system. So you're left with 3 electrons in the sigma bonds, unpaired electron, and you're left with 1 electron in the pi band, which doesn't have a partner. Okay? So what happens to these 4 unpaired electrons? So 2 of them go in a deep state here. So they're populated up and down spins. 1 goes into this dangling bond. So you have a dangling sigma bond that has an electron. And the other one is a state that is sitting in the pi band. So this dangling bond state is a localized state. It's a tightly localized state, and it carries a spin of 1 Bohr magneton. Now the quasi-bound state, it's a little bit spread out. It fits in the pi band, and it typically it has a moment of about between 0.5 and 0.7 Bohr magnetons. Now the pi state here gives you a strong peak at the Dirac point, and this is a 0-mode peak, and it's a consequence of the broken sublattice symmetry. Now, when you break a sublattice symmetry more by adding charge, this peak is going to very fast move down into the negative energy sector. So this is what happens when you plug out a carbon atom. So 2 things happen. First, we have a spin. And the total spin is about 1.7 Bohr magnetons. It could, if you have a high density of these guys, it will go down to about 1.5. The spin from the pi band is green. The 2 spins interact ferromagnetically, so the spins add. And we have a charge. It turns out that at the ground state of the system is where you have about 1 electron positive charge sitting on the vacancy. And this is DFT calculations that shows that this is what's going to happen. So you have positive charge sitting on the vacancy, and this is, of course, compensated by long wavelength Friedel oscillations. So these are the 2 things that we're going to study. So the thing that you can study is the interaction of ultrarelativistic electron with a point charge, interaction of ultrarelativistic electrons with a magnetic moment. How do we study this? We use scanning tunneling microscopy. STM is a very, very simple technique. It's really a high school experiment. You can actually find online a high school experiment that you can build your own STM for $500. So basically what you do, you bring a sharp and of course there's STMs that cost $1 million. And it all depends on how stable you want your signal to be. Ours was closer to the high school price. So you bring a sharp metallic tip to a surface, and you apply a bias voltage till you see a current without touching. And that current depends on mainly on 2 things. One is the density of state of your substrate material, and the other is on the distance between the tip and the substrate. So the dependence on distance is exponential, very, very sensitive to distance. So if you raster, if you keep your current constant and you raster your sample and you have a feedback a motor that makes sure that the current stayed constant, and you monitor the position of the motor, you can get atomic resolution topography of your sample. And this is graphene, and these corners here we have electrons. Another measurement that you can do is we have the density of state here. You can take the derivative of the current with respect to the bias voltage and keep the height constant, and that gives you the density of state, something that's proportional to the density of state as a function of energy. So these are the 2 measurements, basically workhorses of STM. And some of the experiments that we can do, you see this is the topography, beautiful honeycomb structure, spectroscopy in 0 field, you see the linear density of state, vanishing here at the Dirac point, a little bit of an offset between the Fermi energy, which is at 0, and the Dirac point that tells us exactly what the local charge is. You apply a magnetic field, and you see these beautiful Landau levels showing up. This does not happen when you put graphene on silicon dioxide. This sample is graphene sitting on a graphite substrate. It's as clean as you can get it. And you can get also you can measure the Fermi velocity. There's lots and lots of things that you can do. Now, how do we create vacancies? This is a sample before vacancies are there. It's pretty smooth. This is a large scale, so you don't see atomic resolution. And then we bombard it with low energy helium ions, and that creates, that kicks out carbon atoms, that creates vacancies. And most of them, if you're at the right energy, most of them are single atom vacancies. How do we know? We look at the topography here. This triangular structure is a signature of the Jahn-Teller distortion, and if we see a triangle like this, we know that we have a single carbon atom vacancy. So let's go back to what I've shown before. This is the zero mode here, and as I said, when you have charge, this is the zero mode as a function of charge. As you increase beta, this mode very rapidly sinks into the negative energy sector. So a neutral vacancy, the zero peak mode is going to sit right at the Dirac point. Charge vacancy, it shoots down below where we can measure. And then as you keep charging it, you're going to see this, the quasi-bound states starting to show up, peaks starting to show up. So we prepare our vacancy, we see the beautiful triangular structure, we take the density of state, and we expect to see it charged, and the zero mode sits right at the Dirac point. And this is quite amazing. Why isn't it charged? It sits right here. No charge. The theory said that this should be charged. It should have a charge of 1, and here they are completely wrong. I said, okay, maybe they're not wrong. Maybe maybe after plucking out the carbon atom, the system didn't have a chance to reach the ground state, equilibrium. So maybe we can help it a little bit. We could nudge it to equilibrate. So we tried that. So we started pulsing the STM tip into the vacancy, 2-volt pulses for about half a second each. And lo and behold, the zero mode started marching down. It looks like we are actually charging, helping the system reach equilibrium. So it's marching down, and we lost the 0-point mode into where we can't measure anymore. So we can map the charge here onto this theoretical simulation. So we have the charge going from 0 to about half, a beta of about 1/4. And then we continue pulsing, and then there's a new sequence showing up, which you can nicely map onto the 1s state. Now, by the time we got to beta 1.09, we have a new peak coming in, and that's the 2s state. And you see this in yellow here. So we have a 2s, a 1 state, S. We have a 1s prime here, which is a signature of the broken sublattice symmetry. If you brought a charge in without making a vacancy, you wouldn't have this 1s prime peak. So everything works, and it tells us that we have really charged our vacancy. We have atomic collapse. So let's see what these two types of wave functions look like. So when you are in the zero mode peak, it's tightly localized right on the vacancy. It's about 2 nanometer in extent. And when your peaks are atomic collapse peaks, they're huge. They extend 20 nanometers. So there's a very easy way to tell which is which, just by looking at their size. So let's dig into this state here. So I'm going to focus on the largest charge here that we have, 1.09 beta. And starting from the center of the vacancy outwards, we're going to look at we're going to take a density of state as function of position for each one of these peaks. So this is a theoretical simulation. So the 1s is sitting right here, 1s prime, 2s. So here's before we pulsed the vacancy, we don't see anything. After we pulse it and we reach the beta of 1.09, this is the 2s state. So you see an electron cloud sitting right here. This is the 1s prime state right here. And this is the 1s state. And now we see two things. We see a state that's sitting right on the vacancy, but we see a weaker state, a ring around here, a halo around it. And in order to understand what this means, let me plot the Dirac point here. The yellow line here is the Dirac point. The Dirac point always rides on top of the external potential. So if you look at the Dirac point here, everything above the Dirac point is electrons. Everything below the Dirac point is holes. So we have an electron sector here, a hole sector here. In other words, this red thing here is an electron state, and out here we have a halo of hole states. And this will be kind of the equivalent of the positron that's emitted in collapsing atoms. So we have a capture electron state surrounded by a halo of hole state, and it's a mechanism. These vacancies are a mechanism to confine electrons in graphene. Yes?
Just so I can really capture what's going on here, I think you've been describing a scenario in which you're adding electron by electron on by this pulsing process. Is that a fair?
I'm adding what?
Well, your beta parameter,
Uh-huh.
you're not changing the fine structure constant, you're changing Z, right?
No, the fine structure constant is about 1. I'm not changing, no, I'm changing Z. That's right, that's right.
So I should understand every time you run this pulse on the tip, you're adding
Exactly,
electrons.
exactly.
And
The
so
alpha stays constant.
Of how many electrons you're adding?
So that depends on knowing the dielectric constant, which we really don't, because it depends on the screening. So it's not individual electrons, right? So it is not like I'm adding electrons. It's a charge, and it's a continuous thing because it depends on your wave function. So it depends on where you look. So in fact, the net charge over the whole sample is 0, but you have a concentration of positive here and Friedel oscillations that decay. So that's why I use beta rather than charge, and it's not a discrete charge. It is really a continuous charge.
So this is a grounded sheet that you're working with?
No, the sheet is not grounded. Okay. It's not grounded, but I'm not really adding or subtracting electron. I'm redistributing the charge.
I see. You're saying that the cycle is a net zero voltage cycle.
Right.
Kind of no net changes.
Right. Right. So locally, you do have a positive charge. There's no question about it. But far away, there's these weak oscillations where.
But I think I misunderstood. I thought maybe you're stripping off individual electrons.
No, not at all. Not at all. This is not a discrete process. Yeah. So one interesting thing that we can do, we can change the gate voltage, and here's the beta, the effective charge on the hole side and on the electron side. And you see that with the gate voltage, when we're on the hole side, the closer you are to the Dirac point, where you have no screening, the larger the beta is. So this is the maximum beta in this case. But when I gate it and I go into the hole sector, beta is kind of smaller and smaller due to screening. But when I go to the electron side, boom, the whole thing disappears. So you're completely screening your positive charge. So this is a kind of a mechanism to turn the trapping on and off. And we were thinking maybe that can be used to control, to guide electrons in some future kind of experiment. So this is it for the collapse, atomic collapse. And how much time do I have?
About 10 minutes. Reply for questions.
Okay, I can do it in 10 minutes. So now we're going to talk about the magnetic moment. Now, we've known for a long time that when you put a magnetic moment in a metal, the conduction electrons are always going to screen it. So when you go down to sufficiently low temperature, and you have some coupling, some antiferromagnetic coupling between the conduction electron and the spin, eventually, when you're sufficiently cold, you're going to form a cloud of opposite spin electrons around that moment. It's going to be completely screened. So that is known as Kondo screening. It's been known for almost like 90 years now. And this always happens when you have normal metals where your density of state is roughly constant. Now, there's three signatures of having this effect going on. The first signature is the resistance minimum. So normally, when you cool a metal, the resistance keeps going down, and it's saturated at some point. If you have Kondo screening, there is a minimum here. And then where it starts going up. And what happens is when you form that cloud, this is a correlated state, correlated electron state. You form that cloud, there's very strong scattering of that cloud. And therefore, after you form it, you get a rise in the resistivity, scattering from the Kondo cloud. And there are all sorts of very interesting properties. There is scaling with T over Tk, so everything, all these curves can obey, you have logarithmic scaling, so you can tell from the scaling that there's Kondo screening going on. The second signature is in magnetization. So you start out with Curie magnetization, and when you form the Kondo, when you screen your moment, magnetization flattens out. So that's the second signature, flattening of the Curie curve of magnetization at low temperatures. So again, you have scaling with T over Tk, logarithmic correction to the Curie temperature. There's a whole slew of phenomena. And the third signature is the cloud itself. So when you have this large concentration of electrons that screen the moment, you're going to get a peak at the Fermi energy in the density of states. And the peak is pinned to the Fermi energy, and the width of the peak is a direct measure of, it's a Fano line shape, and it's a direct, and from it you can extract the Kondo temperature. So these are the three main signatures of what's going on when you have Kondo effect. What we are going to do is going to look at this peak here. There's a density enhancement at the Fermi energy due to screening. So I should talk about previous experiments on vacancies in graphene. So back in 2011, there was a Nature Physics paper from one of your former colleagues, Michael Führer.
Ellen Williams and Michael Führer.
Right. So, and they've done this pioneering experiment where they, just as we did, they bombarded graphene with ions, and they created single atom vacancies, and they measured the resistivity. And they saw a resistivity minimum, they saw scaling with Tk, they even saw, so this is something I'm going to talk about later, so Kondo screening in graphene. And this was a big surprise because, as I'll show you later, you cannot have Kondo screening in graphene. But here they come, here's experimental evidence. A year later, in the same journal, a Manchester group measured the second signature of Kondo screening, magnetization. So they looked at the temperature dependent of magnetization in graphene. Of course, for magnetization, you need large samples. They use big laminates, and they use squid magnetometry. But they came out with the verdict that there's no Kondo screening. They went out to the lowest temperature and Curie behavior all the way down, no Kondo screening. And then there's a whole bunch of theorists. We came out on the side of the Manchester group, and they were saying all sorts of nasty things about the transport experiment. So since we really try to stay away from controversy, we decided to do STM on this system. One thing to keep in mind is that these two measures measure totally different things. In the resistivity measure, you measure the Kondo cloud. So you measure those moments that are screened, whereas the magnetometer measurement, you're only sensitive to the moments that are unscreened. So we are looking at different things, and this plays a role. Okay, now one other thing to point out is the Kondo screening in pseudo-gap system is a very different beast. So in normal metals, you always have Kondo screening, as long as you have infinitesimal coupling, antiferromagnetic coupling. However, when you have pseudo-gap systems where the density of state is some power law of energy, in particular linear in energy is the case of high TC superconductors or graphene, Kondo screening is very delicate. There is a critical coupling below which you will not have Kondo screening. And this is a plot here. So there's a chemical potential. Kondo screening depends on the chemical potential. If you sit at charge neutrality, there's a critical coupling constant above which you have Kondo screening, and it's asymmetric Kondo screening, and below which you don't. So it depends also on chemical potential here, whether you have it or not, and depends on how strong the coupling is. So here's our experiment. This is a single atom vacancy. Far from the vacancy, we see this linear density of state, kind of has a minimum at the Dirac point. And now we are going to the center of the vacancy, and we see a new peak appearing right at the Fermi energy. So this is our zero mode, which signals the vacancy, and this is a peak, which is a candidate for Kondo screening. So in order for it to be a Kondo peak, it needs to be pinned to the Fermi energy. But since we can move the Fermi energy, we could check that. So here we change the position of the Fermi energy. We increase the chemical potential here. We're sitting in the whole sector, and we're moving toward the Dirac point. And you see there is a peak here that is right at the Fermi energy at all chemical potentials here. So this is our Kondo peak candidate, and this is our zero mode, and the distance between the two measures the chemical potential. And then we can keep going and keep increasing the chemical potential. And you see that you keep increasing it and then increase more, and then the Kondo peak disappears. No more Kondo screening. And then you keep going on the electron side, and it appears again. So we have a reentrance of the Kondo peak. From the line width here, we can measure the Kondo temperature. It is quite large. And they can be 70 Kelvin. We can even get to 180 Kelvin Kondo temperature. So on Kondo, on screening of the magnetic moment, off, which means magnetic moment, unscreened, and screened again. So we have a reentrance behavior. Now, how to interpret this? So this behaves as if we have a critical, the coupling constant is less than the critical coupling. So that's why we have a reentrance. So at the Dirac point, there is no Kondo screening, but when we move out, we final chemical potential. We do have Kondo screening. And instead, this is kind of neat because you have an electrically tunable magnetic moment. You can turn it on and off with some gate voltage. And this is a phase diagram which our theory collaborators have done with numerical renormalization group. Chemical potential is a function of the ratio between the coupling and the critical coupling. Blue region here is you have a local moment. Pink region here is Kondo effect. And our data before, all we have to do is place our data here, and we can figure out what the coupling constant is. So we have a 0.8 JC coupling constant. And then we did a whole bunch, hundreds of vacancies. And we got all these results. We're all over the map. So it looks like the coupling constant is all over the map. So what determines the coupling constant? So in order to understand that, we have to go back to this. And again, remember there were two spins there. There's the sigma spin. And if you have a flat graphene sheet, it's orthogonal to the screening electrons, to the pi electrons. If they're orthogonal, you cannot possibly have screening. So there's no screening of the sigma moment. What about the pi moment? The moment of this other one, it turns out, and if you do the calculation, the coupling is ferromagnetic, no screening. So indeed, there is no Kondo screening in graphene. There shouldn't be any Kondo screening. So what are we talking about? The theorists tell us there should be no Kondo screening. And that's why the Fira paper was so much criticized. The criticism was the theorists said, we showed in this paper there's no Kondo screening in graphene. Therefore, what you see must be wrong. You're misinterpreting. You're really looking at some weak localization. So what's going on? It turns out that if you take the sigma orbital out of the plane, you do get coupling. You do get coupling, which is proportional to the projection of the sigma electron onto the pi electron. And the coupling, it goes like this as a function of angle. So if you're able to tilt your sigma orbital out of the plane, you can actually induce Kondo screening of the of the moment in the sigma orbit. So let's see. So if you have a corrugated substrate, then at every position this angle will be different. So every vacancy would see a different J. So therefore, you really need a local measurement to tell this, to actually discern this physics. So then we tried a bunch of substrate. Graphene on silicon oxide, which is this red here. This is the corrugation height. It's huge, the corrugation. And indeed, we found Kondo temperatures that are as high as 180 degrees, and most vacancies showed Kondo screening. Then we superposed 2 layers of graphene, one on top of each other, on silicon dioxide. There, the screening is much better. It's much flatter. This is the black line here. And we got Kondo temperature of 70 K. This is the data that I show you. 30% of the vacancies show the screening. Then you go to really flat substrate, graphene on boron nitride, or 2 layers of graphene on boron nitride. None of the vacancies exhibit Kondo screening. So in fact, there's really no controversy. The Fura's group was looking at the graphene on silicon dioxide. So it's basically this kind of sample. And there was a lot of the vacancies were screened, and his resistivity measurement measured that. Now the Manchester group was looking with magnetization. They couldn't see the Kondo screening. They only saw the spins that were not screened. And since this is a global measurement, you measure tens of thousands of spins, you average over the whole thing, there's no way to tell that there is any Kondo effect there. So therefore, I think that this kind of reconciles the 2 experiments. And this brings me to my summary. So what I showed you that vacancies in graphene can host a supercritical charge, which display a sequence of quasi-bound state which resemble an artificial atom. The charge is gate tunable, and it could possibly enable electrostatic control of carriers in graphene. And in the second part, I showed you that the vacancy moment in graphene could be Kondo screened, provided that we have sufficiently if you have a corrugated substrate. And again, the moment of the vacancy can be again controlled electrostatically by applying a gate voltage. Thank you for your attention.